So good morning, everyone. So welcome to Physics by Physics. And in this C.T.P series, we are going to focus on the concept of electrostatic energy. That is the part of electricity and magnetism, or E.M.T. So we will see concept of electrostatic energy, and then we will solve some problems related with that concept. So let's see. We will talk about electrostatic energy. So again, we will take problems from our QIP file, QIP series. As you know that we are running our QIP series, in which we have compiled last 15-20 years question of different exams, and we have arranged it in topic wise. For example, in electrostatics, now this file is for work and electrostatic energy. So in this particular file, you will learn concept of work and electrostatic energy. So what is the work done in moving a charge Q, and what is the electrostatic energy? So let's see. I will just give you the basic concepts, and then we will focus on problems. So let's see if you have some arrangement of charges. And at any point P, there is a electrostatic field E. This is the field E, and you want to move a test charge. I'm assuming this is positive, test charge is also positive, and you are moving this test charge from point, let's say this point is P1 to point P2. So you have to apply some external force. Let's say this is external force. So work done in moving charge Q from P1 to P2 is given by, similarly, F external dot dl, and you want to move it from P1 to P2. And this force is, because in this direction force is QE, so this force is minus Q into E. So I am taking P1 to P2 is minus Q into E dot dl. And you know, by definition, minus E dot dl P1 to P2 is potential difference between 2 points. This is simply depends on potential at P2 minus potential at P1. So work done is independent of path. And we say that electrostatic field is conservative in nature. Work done is independent of path. If I am taking point P1 to be at infinity, where we will assume potential at infinity is 0. And if you are moving charge infinity to this point, we will write this is the work done. And if you are taking this point to be R, so work done in moving charge is, this is the work done in moving test charge Q from infinity to a point where potential is VR. And this work done is stored as its electrostatic energy. So if you assemble two charges, this is the work done, and that is the electrostatic energy, because that is total work done in assembling all charges. And electrostatic energy of set of, let's say, n charges is total work done in assembling all n charges. So let's see what is total work done in assembling n charges. And this is called as electrostatic energy. This is called as electrostatic energy. And this is given by W1 plus W2 plus and so on Wn. Just find if you place first charge, then there is no other charge. So we will always take work done by placing first charge to be 0. So you have to just find total work done in assembling all charges. So that will give you the electrostatic energy of set of n charges. And we can write this as, this is given by 1 by 2 summation over I, or this is Qi. Let's write in this form. This will be given by 1 by 4 pi epsilon naught Qi Qj Rij I1 to n and J1 to n. Here I greater than J or I less than J. Both conditions are allowed. But if you are considering that both pairs are allowed, so in that form it is given by, you have to take 1/2 sign. I1 to n, J1 to n, 1 by 4 pi epsilon, 1 by 4 pi, 1 by 4 pi epsilon naught, Qi Qj by Rij. Here only thing is I is not equal to J. So this is the total work done in assembling n charges. Now we have to see electrostatic energy for continuous charge distribution. So for continuous charge distribution, electrostatic energy is given by epsilon naught by 2 E square d tau volume integral all space. So we have to, this is the electrostatic energy for continuous charges. And there are two standard result electrostatic energy for spherical shell. So that will be given by, I am giving you the result Q square by 8 pi epsilon 0 R. What is a spherical shell? Where you have a shell of radius R and charge Q is uniformly distributed over it. And another example is uniformly charged dielectric sphere. Uniformly charged dielectric sphere. So if you have uniformly charged dielectric sphere, this radius is R and charge is distributed throughout the volume. So in this case, it is given by 3Q square by 20 pi epsilon 0. So these are the standard result that you have to remember. Clear? So we are going to discuss problems based on these concepts. So in this file, we will take these concepts only. So that is the summary for this topic. Now see, let's take question number 2. Question number 2. Solve question number 2. Let's solve question number 2. So you have a small charged spherical shell of radius. It's a shell of radius 0.01 meter. At a potential is 30 volt. This potential is given. The electrostatic energy of the shell. So you know that electrostatic energy of a shell is Q square by 4 pi epsilon 0 R. But here potential is given. So what will be potential? Potential is Q by 4 pi epsilon 0 R. So charge is not given. So we can replace charge by E. This will give you Q is 4 pi epsilon 0 R into V. So this is 4 pi epsilon 0 R whole square V square by 4 pi epsilon 0 R. So what will be electrostatic energy? 4 pi epsilon 0 R into V square. Now you should calculate this value. This is electrostatic energy is 8 here. You have to take here 8 value, not 4. I have written the formula, so you should take. So here you should write 2. So this will give you 2 into this value. This will be not like this. Potential is same value, but here you have to write 2 times of 4 pi epsilon 0 R. So what you will get? I have replaced this. Now I am taking here 1 by 2 because this is given by 4 pi divided by 2 into 4 pi epsilon 0 R. This will be square. So this value is 1 by 2 4 pi epsilon naught into R into V square. So 1 by 2 4 pi epsilon naught is 1 by 9 10 to power 9. R is given as 1 into 10 to power minus 2 meter. And V is given by 30 whole square. So this value will be 1 by 9 10 to power 9. This is 900 10 to power minus 2. So 9 and 00. So this will cancel out. Now this will give you 1 by 2 10 to power minus 9 because this 9 will cancel out. And you will get 0.5 into 10 to power minus 9 joules, or this will be 5 into this much joules. So option B is correct. 5 into 10 to power minus 2. So here answer is B. 5 into 10 to power minus 10 joules. Clear? So note it down. Give me 1 minute. Hello. हाँ क्या हुआ? हाँ फ्रेंड से कुछ आ रहा है क्या? हाँ चलो बता देते हैं। तो कई बार ऐसे हाँ ये अभी देखो एक मिनट। So now we will see next question. Let's see next question. So next question is question number 3. So what is the work done in moving -5 microcoulomb charge in an electric field E from a point A to B? So R is fixed, theta is changing. So what will be work done? Work done is given by what? F dot dl. So let's see question number 3. In question number 3, so work done is given by F external dot dl, and this is minus Q into E dot dl. Now charge is given as -5 microcoulomb. So you can write it as minus of -5 into 10 to power -6 coulombs. What will be electric field? Now I will take spherical symmetry. So this is 8R sine theta r cap plus 4R cos theta theta cap dot dl is in spherical symmetry. If you write, this is dr r cap plus r d theta theta cap. So you will get 5 into 10 to power -6 coulombs, and this will give you what? R dot r is 1 and theta dot theta is 1, r dot theta 0, theta dot r 0. So you will get 8r sine theta dr plus 4r square cos theta d theta. Now from A to B, point A is what? 10 and pi by 6. And you are moving to point B. Point B is 10 and pi by 2. So here R is constant. So when R is constant, R is 10. This constant value is R is equal to 10, that is constant value. So dr will be 0. So when dr is 0, this first term is 0. Now you should put r here and integrate with respect to theta. So this is 5 into 10 to power minus 6 into 4 into 10 square. This is common value. And now you have cos theta d theta. So this is pi by 6 to pi by 2 cos theta d theta. Now this will give you 20 into 10 to power minus 4. And this is cos theta is sin theta. Cos theta will be sin theta. So this is 0 to pi by 2 to pi by 6, pi by 6 to pi by 2. So this will give you 20 into 10 to power minus 4. And you have sin pi by 2 minus of sin pi by 6. So sin 30 is 1 by 2. So this value is 1. Sin 90 is 1. And this value is 1 by 2. So this is 10 into 10 to power minus 4. So this is 10 to power minus 3 joules, or this can be written as 1 millijoule. So which option is correct? So option C is correct in this case. So in this situation, answer is 1 millijoule. So option C is correct. Question number 3, option C is correct. Clear? Now let's see. One question is question number 4. For discrete charges, try to solve question number 4. Solve question number 4. Solve question number 4. 3-point charge, each carrying charge Q, are placed on the vertices of an equilateral triangle of side L. The electrostatic potential energy of this configuration. So let's see question number 4. So you have let's place first charge here. This charge is Q. So I'm taking this to be a first charge. So what is work done in placing first charge? 0. Because there is no other charge here. And then in presence of first charge, you are placing the second charge. This will be L. So W2 is given by work done in placing second charge will be Q into potential due to 1. And this is given by Q into Q by 4 pi epsilon 0 L. So this is Q square by 4 pi epsilon 0 L. Clear? You have to find total work done in assembling all charges. That is the electrostatic energy. Now you have question number 3. This charge number 3. So when you place third charge, work done is given by V1 plus V2. So V1 plus V2 is given by V1 is Q by 4 pi epsilon 0 L, and V2 is also Q by 4 pi epsilon 0 L. So this will be what? 2Q square by 4 pi epsilon 0 L. So what is total work done in assembling these 3 charges? Total work done in assembling these 3 charges. This will be given by W1 plus W2 plus W3. So if you add these two, so you will get 3Q square by 4 pi epsilon 0. So option C is correct. So in this question, option C is correct. Clear? Now let's see question number 8 or question number 7 and then 8. Let's solve 7 and 8. Try to solve 7 and 8. Question number 7. So consider 2 concentric spherical shells. So what do you mean by concentric spherical shells? It's a thin spherical shell. So center is common and this radius is A and this radius is B. Inner one carries charge Q. So charge over it is Q. And outer one carries charge minus Q. And both of them are uniformly distributed over the surface. So distribution is uniform. So you can easily write the electric field due to this charge configuration. If you know electric field, then you can find electrostatic energy of this particular configuration. So let us first write what will be electric field in the region R less than A. So this will be 0. According to Gauss law, this will be 0. Now if you are taking region R to B, in this region, so this will be because of the inner shell, E2 is given by 1 by 4 pi epsilon naught Q by R square R cap. So in this region, field is E1, that will be 0. Here field is E2 and here field is E3. Now for R greater than B, what will be E3? According to Gauss law, total charge enclosed will be 0. If you draw a Gaussian surface, charge enclosed is Q plus Q minus Q, 0. So electric field outside will be 0. So now how to find electrostatic energy? We know the formula for this is epsilon naught 2 E square d tau volume integral all space. All space means you have to integrate 0 to infinity. So now, because there are 3 different regions, so we will write this equation accordingly. So first will be E1 square and d tau I am writing 4 pi r square dr. This is 0 to a. Second term will be epsilon by 2. This will be a to b E2 square 4 pi r square dr. And third region epsilon naught by 2. Now it is b to infinity E3 square 4 pi r square dr. Now E1 is 0, E3 is 0. So you have to write only this term. So this will be given by, you will get 4 pi epsilon naught by 2 common here, because you have to write E2 square. So E2 square is Q square by 4 pi epsilon naught r square whole square, and here you have r square dr. So this will give you what? 1 by 4 pi epsilon naught square. So here you will get 1 by 8 pi epsilon naught. Because 4 pi epsilon naught will cancel out 2, and this is 1 into Q square and integral 1 by r square dr, and this limit is b to infinity. So this will be Q square by 8 pi epsilon naught b to infinity. So this is minus 1 by r b to E2 is a to b. Please correct it, because this is a to b. E2 is a to b. Integral is from a to b. So this will be also from a to, integral is a to b. So this will be a to b. So now you will get Q square by 8 pi epsilon naught, and you have 1 by a minus 1 by b. So just see, option A is correct. So answer is option A. So question number 7, option A is correct. Now this is last question. Let's try to solve it. Now solve question number 8. So you have to find electrostatic energy per unit length of the system. It's a very long cylinder. Inner one carries charge plus lambda and outer one carries minus lambda. So you know field due to long wire. It's a case of a long wire. So question number 8. So what is the field? Again, in this situation, I am writing field when R is less than R1. Field will be 0. Because if you draw any Gaussian surface, in this region, if you draw any Gaussian cylinder, charge enclosed will be 0. But when you are considering R1 to R2, then E2 will be given by, long case of long wire, lambda by 2 pi epsilon 0 R cap. And when you are taking region R greater than R2, because this one contains plus lambda and minus lambda. So if you consider a Gaussian cylinder, electric field will be 0. So again, you have same formula that you have to use. Now I am going to use same formula, but E1 and E3 will be 0. Only this term will survive. Only this term will survive. So I am directly writing. So if you write this, you will get epsilon naught by 2 E square d tau volume integral all space. Because E1 and E3 will not survive, so I will write only E2. So this is E2 square. Now it's a cylindrical symmetry. So d tau is what? 2 pi RL dr. Where I'm taking L is the length of the cylinder. So what will be, limit will be what? R1 to R2. Because you have to find electrostatic energy per unit length. So I'm writing this equation as 2 pi epsilon naught by 2 R1 to R2. This is lambda square by 2 pi epsilon naught R whole square into R dr. So this will give you lambda square by 4 pi epsilon naught. This is 1 by R dr. R1 to R2. So finally, electrostatic energy per unit length will be lambda square by 4 pi epsilon naught ln R2 by R1. ln R2 by R1. So if you see electrostatic energy per unit length, so option C is correct. Option C is correct here. So we have discussed concept of work and electrostatic energy. And if you see in last 15 years, they have asked you only these type of question. Even I have taken NET, GATE, JAM, JEST, all type of possibility. So if you solve this particular file, you can easily solve question related with work and electrostatic energy. So that is the purpose of our QIP file, so that you must be able to solve question related to one particular topic. If you know the concept and if you have solved the previous year questions and other possible type of question that may be asked on that particular topic, so you can easily handle any question during exam condition. Clear? So that is the purpose of our QIP, and in C.T.P also we are focusing on same method. Clear? So next topic is we will talk about properties of conductor. So that we will discuss in next C.T.P series. Okay? Okay. Thank you everyone. Thank you.